Hello everyone, this is Dr. Webb. In the last abstract algebra video, we introduced the concept of cosets, and then we used that to prove a very important result called Lagrange's theorem. In this video, we're going to be looking at some important consequences of Lagrange's theorem. So let's refresh ourselves on Lagrange's theorem. If G is a finite group and H is a subgroup of G, then the order of H divides the order of G. Moreover, the number of distinct left or right cosets of H and G is going to be precisely the order of G divided by the order of H. And if you recall, this all comes from the fact that when we break G into cosets of H, these cosets, they are really an equivalence relation on the elements of G. And so these different cosets form a partition of G, and they're all the same size. And so the number of cosets is times the size of each coset, and the size of each coset is H, is going to give us all of G, because every element is inside exactly one of them. And so then this leads us to this definition of index, which is that if G is a group and H is a subgroup of G, then the index is the number of left or right cosets. And we write it G colon H, usually. Okay, so let's start proving some immediate results from this. So first of all, if G is a finite group and A is an element of G, then the order of A has to divide the order of G. And so this comes from the fact that the order of A is equal to the order of the cyclic group generated by A. And this is a subgroup inside of G. And so by Lagrange's theorem, this divides the order of G. And so it's as simple as that. The order of any element of the group has to divide the order of the group. What this then means is that if G is a finite group and A is in G, then if you raise A to the order of G, you are going to get the identity. And this comes from the fact that since, by the previous one, since the order of A divides the order of G, then if you look at A to the order of G, this is going to equal A to the order of A raised to some kth power, and A raised to the order of A is the identity. Okay, where K here, K is going to be equal to the index of the cyclic group generated by A inside of G. Okay, and these are two very important results here, because it means that now if we have a group and we know exactly what its order is, it really cuts down on the possible orders of elements that could be inside of that group, if the only possible orders are divisors of G. Okay, now going along with this, in particular, if the order of G is prime, then G is going to end up being cyclic. And the idea here is that if the order of G is some prime P, and A is inside G, A is not equal to the identity, well then the order of A has to equal P, and that's the order of the cyclic group generated by A. And so the cyclic group generated by A has P elements, and so then the cyclic group generated by A has the same number of elements of G, so it must be all of G. Okay, so really this actually proves more than this, that if you have a group G and its order is prime, then not only is it cyclic, but it's actually generated by every non-identity element of G. So if you take anything of order 17 that's not the identity, it actually is going to generate the entire group. Okay, going along this way, let P be prime and take any integer A that is relatively prime to P, then the order, if you raise A to the P minus 1 power, you're going to get something that's congruent to 1 mod P. Okay, and this is, again, this is using Lagrange's theorem, and the idea is that if the GCD of A and P is 1, then that means that A is congruent to some R mod P where R is between 1 and P minus 1, right? And if R is between 1 and P minus 1, then we can think about R as being in the multiplicative group, mod P, and the multiplicative group, mod P, its order is P minus 1. So R to the P minus 1 is going to equal the identity in Z mod PZ, but the identity in Z mod PZ is 1. So R to the P minus 1 is going to be congruent to 1 mod P, because that's the identity in Z mod PZ star. And A to the P minus 1 is congruent to R to the P minus 1, which is congruent to 1 mod P. Okay. And again, this right here, R to the P minus 1 is congruent to 1 mod P, because R to the P minus 1 is the identity in Z mod PZ star, and the identity in Z mod PZ star is 1. Okay. Now, an immediate result of this is a very famous and important theorem in number theory called Fermat's Little theorem. And what Fermat's Little theorem says that is if you take a prime p in any integer a, then a raised to the power p is going to be congruent to a again, mod p. And so the idea of this is if p divides a, then a's congruent to 0 mod p, and a to any power is still going to be congruent to 0 mod p. And so that's kind of a trivial case. On the other hand, if p does not divide a, then the GCD of a and p is equal to 1. So a to the p minus 1 is congruent to 1 mod p by the corollary above. And then if you multiply both sides by a, you get a to the p is congruent to a mod p. And that gives us our result. And what's interesting about Fermat's Little theorem is that Fermat was in the 1600s, and for a long time, mathematicians just thought that this was sort of a fun little result in number theory. But in the last 50 years, this has become very important for what's called public key cryptography, which is how people essentially send encoded information to each other over the internet. And so this has been this little result seems kind of silly and kind of simple, but it's actually incredibly important in the modern world. The last result that we are going to be talking about involves what are called orbits and stabilizers. And so for these, we're going to think back to groups of permutations acting on some set. And so if you have G as a group of permutations acting on a set S, then for any I in S, anything in the set, the stabilizer of I in G is all of the elements of G that fix I, so it's all the alpha in G such that alpha of I equals I. And so again, this is called the stabilizer of I in G. We actually had a homework problem on this previously, where we proved that the stabilizer of I in G, so all of the elements in G that fix I, is a subgroup of G. Then the orbit of I, this is equal to all of the elements of S, so S in S, such that S is equal to gamma of I for some gamma in G. Right? So really the orbit of I is all the things that I get sent to inside of S by the elements of G. Okay, and so stabilizer keeps I in the same place. The orbit is all the other possible things in the set that I might get sent to by elements of G. Okay, so the theorem stemming from this, which is called the orbit stabilizer theorem, and this actually tends to be important in a number of different areas. One thing, if you say go keep studying algebra in graduate school, this becomes very important in what's called the CELO theorems, which really lets you dive a whole lot deeper into exactly what type of subgroups a group can have. And so what the orbit stabilizer theorem says is that if G is a finite group of permutations on a set S, then for any I in S, we have that the size of the group is equal to the size of the orbit of I times the size of the stabilizer of I. Okay. And so the important thing in proving the orbit stabilizer theorem is this lemma, which is going to bring this back to cosets. And it says that if it's for any beta and gamma in G and any I in S, then beta of I equals gamma of I if and only if the coset beta times the stabilizer of I is equal to the coset gamma times the stabilizer of I. And so this is what's pulling this back to Lagrange's theorem and to cosets. And so the proof of this is, for the first direction going forward, if beta of I equals gamma of I, well then I can plug both of these into gamma inverse. And so we'd have gamma inverse of beta of I is equal to gamma inverse of gamma of I. But gamma inverse of gamma of I, this is just the identity permutation on I, which is just I. So this means that gamma inverse of beta fixes I, so it is inside the stabilizer of I. And so then this means that gamma inverse of beta is equal to some alpha in the stabilizer. And so then beta is equal to gamma alpha. And so it is inside gamma times the stabilizer. And if beta is inside gamma times the stabilizer of I, then since this is a coset, gamma times the stabilizer of I is a coset, and cosets are equivalence relations, this means that the two cosets are the same. And so this finishes the proof in that direction. Now let's erase this and prove the other way. Now the proof in the other direction is essentially going backwards for the other proof. And so if beta times the stabilizer of I equals gamma times the stabilizer of I, this means that beta is equal to gamma times some alpha, where alpha is in the stabilizer of I. And so this means that beta of I is equal to gamma of alpha of I, but alpha's in the stabilizer of I, and so alpha of I is just I again, and so beta of I is equal to gamma of I. And we're done. Okay, so now that we have the lemma, now we can prove that, that these two are the same. And so by Lagrange's theorem, since the stabilizer of G is a subgroup of G, then G is going to be equal to the index of the stabilizer in G times the order of the stabilizer. And so remember this index, this is the number of cosets. And by the lemma, each of these cosets are sending I to a different place. So by the lemma, each coset corresponds to a different place where I is sent, and so that corresponds to the different elements. The different elements of the orbit of I, and so the number of cosets is the number of things in the orbit, and so this right here is equal to the orbit of G in I. And that completes the proof. That is all for this video. I will see you again soon.